Hey, welcome everybody. Comment on pump curves and analyzing head loss in a pumping circuit. So John Siegenthaler is our guest today, and he's going to present some information about analyzing the performance of a circulator in the hydronic system, just as it says here. This is going to be really informative. I know he's got a lot of slides to go through, so I'm going to have him just zip through the housekeeping here at the front end, and we'll have it a little bit more at the bottom end of it too. So thanks, John, for joining us.
You're welcome. Good to be here.
So here's where we are with Hydronics. That's what's out there currently right now. If you're not receiving these, let us know. We'll make sure we'll get you on the mailing list so you get these in the mail every time we have a new issue coming out. So that's 15. And, of course, next week we'll be up in ASHRAE in Chicago, and that's where we'll have number 16, which ties in nicely to the subject today. So 16 will be available on the show floor. If you do have a chance to come by and see us in the booth in the McCormick Center up there next week, we'd love to say hi. So that's what we've got for the next issue, number 16. So I think I'm just going to turn it right over to you, Siggy, so I don't get on a roll here.
Sounds good, Rod. Good to be with you today. We've got quite a few topics to get through. I won't read all these to you, but these are all topics that we do cover in that latest issue of Hydronics, number 16. We're going to get a taste of some of these today, and again, I encourage you to get that issue and read through it in more detail. I'm going to start with a quick review of what we talked about back in December. We were talking about the concept of head and specifically head loss in hydronic systems. So just as a quick review, just to define what head is, in the context of hydronics, the best description of the word head is mechanical energy that the fluid contains. And short and sweet, circulators add head energy to the fluid. Everything else that fluid goes through removes that head energy, and we're going to see more of the head added side today. If you're interested in kind of the physics of it, we could look at head as the foot-pounds of mechanical energy that a circulator imparts to each pound of fluid as it passes through that circulator. And if you look at this kind of mathematically, you could cross out the units of pounds, and that's where we end up with this unit of foot. And I know that used to confuse me. When I hear the unit of foot, I think about distance. And I think probably the most useful way to think about the units of head energy is this over here. It's the foot-pounds of mechanical energy added to each pound of the fluid. Now, another useful concept is to think about circulators as energy converters. The intent of a circulator is to take electrical energy as its input and convert that to head energy. So we'll look at this little circulator here. We're going to put electrical energy in to run it, and it's going to create and impart to the fluid what we call head energy. And if that circulator was 100% efficient, excuse me, it would convert 100% of that electrical energy into head energy, but they aren't, and we're going to look at that efficiency in more detail. So one of the byproducts we get due to the inefficiency of a circulator is heat. Now, oftentimes when we're talking about hydronics, we talk about head and we talk about pressure, and as we talk about it, we tend to use these terms a little loosely sometimes. Head and pressure are related, but they're definitely not the same thing. It's sort of like the relationship between heat and temperature. They're definitely related, but they are distinctly different. So here's a good working understanding of the difference. An increase in pressure in a fluid is the evidence that head energy has been added to that fluid. And we're going to see that if we put pressure gauges on each side of a circulator. Now, the opposite of that is also true. A decrease in pressure is the evidence that head energy has been removed from the fluid. We don't have any way to directly measure head as a separate entity, but we can measure it by watching how pressure either increases or decreases. So here's a graphic actually right out of Hydronic 16. Here's a circulator, and if we look at the pressure on the inlet of that circulator, it's 12 psi. And on the outlet, it's 18 psi. So we have an increase in pressure of 6 psi. That's the evidence that we're adding head energy. Down below, we've got a collection of components here. And this could represent basically everything else in the system other than the circulator that fluid moves through. Piping, fittings, valves, heat exchangers, boilers, heat emitters. And again, I've kind of lumped them together as components, but the idea here is we have 10 psi on the inlet, 7 psi on the outlet. That's a drop in pressure. Again, that's the evidence that we have dissipated head energy. And mathematically, there's a relationship between the change in pressure that you would observe, either an increase across the circulator or a decrease across the piping system. To get the relationship between the change in pressure and the head that's either added or removed, we need to know the density of the fluid. It's not as simple as just a constant. For example, sometimes as a rough approximation, people will sometimes take this to be about 0.43 and take 0.43 times head equals delta P. Well, that's actually only true for cold water, water at about 60 degrees. If we're dealing with heated fluids or we're dealing with fluids other than just water, such as an antifreeze mixture, we need to know the density, and the density is actually dependent on the temperature. So we need to know approximately what's the average fluid temperature in the system, look up the density, and then divide by 144, and then we can easily convert between delta P and head. Now, again, a review from what we talked about back in December. We talked about piping circuits and something called a circuit head loss curve. And I made a statement that every piping circuit has a circuit head loss curve. It's just a matter of determining what that curve is. We can think of that curve as almost a fingerprint for that piping system. So again, as a review, we take a look at this circuit. And let's take the circulator out of the picture now and just look at the pipe, the fittings, the valves that are present. We can analyze that using the methods we talked about back in the December Coffee with Caleffi presentation, and we can come up with a circuit head loss curve. Mathematically, it would look like this as a formula, and if we plot out a few points where we take flow rate, calculate head loss, the characteristic of the curve is it starts at zero head loss, at zero flow rate down here, and it gets progressively steeper as we go to higher flow rates. Now, there are curves associated with circulators. We call them pump curves. And let's take a look at a pump curve here. Here's a typical small wet rotor circulator that you might find as, for example, a zone circulator in a residential system. You'll see, first of all, that the curve goes in kind of the opposite direction of a system curve. Okay, it starts high, and as we go to the right, it goes down. The system curve starts low, and as we go to the right, it goes up. And this curve is representing the head added to the fluid. And again, think of head as the foot-pounds of mechanical energy added to each pound of fluid that's passing through. And that number, that amount of energy added to each pound, varies with the flow rate. The maximum foot-pounds per pound is added at zero flow rate, and then as we progress to the right here at higher flow rates, we add progressively less foot-pounds per pound to it. And every pump has a curve. If it's a single speed pump, it has one curve. We're going to see that as we get into variable speed pumps and multiple speed pumps, that we have, for example, a separate curve for each speed. Just some terminology here. Again, we're plotting head added on the vertical axis against flow rate on the horizontal axis. The point where the pump curve touches the vertical axis, we call that the deadhead condition. That's what would happen if you had an operating circulator and you simply closed down a valve on the discharge side. There's really no point in doing that. The circulator's impeller just spins and basically dissipates energy into the fluid. You have zero flow rate there, but that's the maximum head added point. Over on the far right, you see what's called the runout point. That's, in theory, where the flow rate would be maximum pumping against zero flow resistance. And a general statement here is you want to avoid operating a circulator at either of these conditions. You could operate a circulator up here, but there's really no point in it. It's basically just dissipating electricity into heat. In general, you're going to see we want to operate the circulator ideally in the middle third of its pump curve. That's where we're going to get the best efficiency. Now, most circulator manufacturers have what I call a family of circulators. These are related size pumps, some of them bigger than others. and it's common that they will plot these pump curves out on a common graph so that you can make comparisons between them. So just as an example, here's some curves from Grundfos with the model numbers over there. Here's some curves from Armstrong. You'll also find curves from like Bell & Gossett, Takeo, and some of the other companies that are out there offering circulators. The nice thing about having a family of pump curves is if you draw the circuit head loss curve on this graph, you can very quickly determine the flow rate that each of these different circulators in this family of circulators would produce, and narrow down your selection from that. And this is really one of the key slides in today's presentation. This is the idea of plotting the system head loss curve and the pump curve on the same graph and looking at where they cross. And it makes perfect sense if you think about the fact that the circulator adds head energy, the circuit that the flow is going through removes head energy, so where they balance each other, in other words, where the head added by the circulator exactly balances the head dissipated by the piping circuit, that's a condition we call hydraulic equilibrium. That's where every piping circuit with a given circulator installed, that's where it settles out after just a few seconds of turning that circulator on. And we can find the conditions at that point very easily. You just find the intersection here, which is called the operating point, and you read down to the horizontal axis to read the flow rate. If that flow rate is close to the flow rate you're looking for in your system, then that circulator is what I call a good candidate to be installed there. If that flow rate is, maybe more than 10% off from the flow rate you're looking for, maybe you want to look at a different circulator. Okay, so the key idea is where the pump curve crosses the circuit head loss curve. That's the operating point, and that's where that system settles out. So here's an example where I've plotted 3 different pump curves there, the red curves. I just label them circulator 1, 2, and 3. Different models, for example, from a given manufacturer, and there's a single system head loss curve there, and you can see that the intersection points are different. If we went with, let's start with circulator number 1 here. We've got this operating point, and it looks like we'd be somewhere around just under 7.5 gallons per minute. If we were to change the circulator to circulator number 2, that's this middle curve, and look at how close these points are. That shows you, even though those 2 circulator curves, pump curves, are quite different from each other, circulator 1 and circulator 2, they actually end up operating at almost the same flow rate in that particular system. We might not know that just by looking physically at the circulators, but this is the advantage of plotting these curves out. Circulator number 3 has a smaller or a lower pump curve, and you can see that would produce a flow rate a little under 5 gallons per minute. So again, think about this concept. And there are software packages out that do this all behind the scenes, but fundamentally this is how you determine what a given circulator will do in a given circuit. Okay. Now let's kind of again review what can change the circuit's head loss curve. Well, there's several things. If you change the fluid that's in there, for example, if I went from water to an antifreeze fluid, that would change the curve. Temperature changes will also slightly change those curves, and that's because the density and the viscosity of the fluid change with temperature. Anything that you would do physically to the piping circuit, if you were to change the pipe size, the pipe type, for example, change from PEX to copper, or the pipe size, if you change the number of fittings, certainly if you change valve settings, all those things have an effect on the circuit head loss curve. And again, just to give you some examples here, here's a typical circuit head loss curve. If we make some of these changes, we might make that curve steeper, or we might make it shallower. Those are just kind of relative terms. This is a situation we don't often see in small hydronic systems. This would be where there's actually what's called the lift head. About the only system where we see that in the context of small hydronic systems is a drain-back solar system where we have to lift the water from the storage tank level up into the collectors, and what that does, that shifts the system curve up. Most of the time, however, we're dealing with this kind of a situation with system curves. So let's ask the same question, but let's ask ask it about circulator pump curves. What can change the circulator pump curve? Well, certainly if we change the circulator, it'll have a different curve. If we change the circulator to a different speed setting, many of the small circulators today have got at least 3 speeds on them. Or if we were to do something to the circulator's impeller. That's not as common today because even small and large circulators have variable speed control. The idea of taking the impeller off and machining it down, I won't say it's gone, but it's certainly less common. But if you did that, if you machined a 1/10 of an inch off the perimeter of the impeller, that is going to change the curve. Here's an example of 3 pump speeds. It's the same circulator, but just with 3 different speed settings, a switch that you would change. And each speed has its associated pump curve. And if you plot the circuit head loss curve against those 3 pump curves, you can see the flow rate that you would get here if you were to operate that circulator at each of these 3 different speeds. Again, it's always where the circuit head loss curve crosses that pump curve. Now, there's another thing you can do if you have pressure gauges involved. You can get a pretty good estimate of the flow rate in a system by measuring the differential pressure across the circulator. And this is a graphic out of Hydronic 16. This shows 4 different ways that you can measure differential pressure across the circulator. You can put a gauge on each side. On a larger pump, you may find tappings right into the flange. If you take a look at some of the larger circulators, look at the flanges, and oftentimes you'll see an 1/8 inch tapping with a plug in it. And the idea is you can take the plug out, install a pressure gauge. If you do that, my recommendation would be to put a ball valve in there so that you could isolate the gauge. If it ever fails, you can change it without shutting down the pump. You can also do this. It's a single pressure gauge with a ball valve on each side tapped in near the intake and the discharge of the circulator. And the idea here is you open one of those valves at a time. One of the nice things about doing this is if there's any absolute error in that gauge, let's say that gauge is reading 1 psi high, well, it'll read 1 psi high when you take the inlet pressure as well as when you take the discharge pressure, and then when you subtract, that 1 psi absolute error goes away. So that's one advantage of using a single gauge. And then finally, there is such a thing as a differential pressure gauge that has 2 tappings. You can pipe that in. Now, once you get that pressure reading, we need the delta P, or the differential pressure across that circulator. You take the pressure at the discharge minus the pressure at the inlet. So in this case, we have 9 psi. Then we have to convert that over to head. Remember that graph with pump curves on it is in head on the vertical axis, not differential pressure. So there's that formula. And I gave you a graph here for water. So we look up, let's say, what the water temperature is on average. And let's say it was 150. We'd read up to the curve. We read over here to get our density. We plug that into the formula. Looks like in this case, I assume cold water density about 62.4. And that converts that 9 psi into just under 21 feet of head. Okay. Step 3 now is to go to your graph that shows the pump curve. Find that head value, just under 21, read over to the curve, and then finally from that point where you intersect the curve, go down to the horizontal axis, and you can see we're just under 10 gallons per minute. Now, keep in mind, this assumes that that circulator operates on that pump curve. There's going to be some manufacturing tolerance. I've asked about that. I've had answers about plus or minus 5%. So a given model of a given circulator, its curve might be very slightly higher, slightly lower than the published curve. So again, this is going to get you in the ballpark. It's not the same as a precision lab-grade flow meter, but it does give you a pretty good idea of what's going on, and it does that without the need of a separate flow meter in the system. So let's change now to another topic, circulator efficiency. And there's a couple ways to look at circulator or pump efficiency. Over here on the left, we're looking at a pretty large circulator. You can see there's no electric motor on that. The shaft goes right out the back here. This is just a coupling assembly. We can talk about the efficiency of converting mechanical energy into head just talking about this type of entity, no motor involved. And we call that pump efficiency. And over on the right, we're looking at a small wet rotor circulator. The motor is an integral part of that circulator. And we're going to talk about what's called wire-to-water efficiency. So that includes not only the mechanical and hydrodynamic losses in the pump, the wetted portion of the pump, but it also includes the efficiency effect of the motor. So we'll start off with the pump efficiency, with this larger one. Pump efficiency is basically this ratio, desired output divided by necessary input. The desired output is head energy added to the fluid, and the necessary input is the mechanical power that we supply to the pump shaft, using whatever as our what's called a prime mover. It could be an electric motor. It could be a gasoline-powered engine. We don't really distinguish as to what is turning the shaft on that pump. We're just looking at the pump itself. And there's a formula, if you know the differential pressure and the flow that the pump is producing, and the horsepower of the device that is rotating the shaft of the pump, you can calculate the efficiency of the pump. And typically you're going to end up with something like this. Now, this is a graph that shows two, it's the same pump with two different motors on it. There's a 1/3 horsepower motor option and a 1/4 horsepower motor option. And you'll see that there are what are called contour lines here, and they're labeled with different percentages. If the pump, for example, happened to operate right here on the pump curve, it would have a 57% efficiency. If it happened to operate, let's say, right there on the pump curve, where the arrow is pointing, it would be 35% efficient. If it's in between these contours, you have to kind of interpolate what that is. Now, if you look around, you'll see there's actually a dot here. This is called the best efficiency point. That's the ideal scenario. If your system curve, or your circuit, I should say, circuit head loss curve, were to come up through and pass right through that point, that would allow that pump to operate at its best possible efficiency, which in this case is 59%. And what does that 59% mean? It means 59% of the mechanical energy that is being supplied right here at the shaft is actually being converted to head energy and transferred over to that fluid. Okay? So again, I want to emphasize, when we talk about pure pump efficiency, we're not including any electrical motor or any other prime mover efficiency. It's just the efficiency of mechanical energy converted over to head energy. Again, if our circuit head loss curve was very steep, we could be at this efficiency point here. If we had a different circuit with this kind of a curve, we would be at that efficiency. And let's see, we would be here at about 45%, looks like about 40% here. But if we happen to have a circuit head loss curve that looked like this and it passed right through that point, we would be at 59% efficiency. So again, the goal as a designer is to try to keep the intersection between the circuit's head loss curve and the pump or the circulator that you select reasonably close to the center of that pump curve. That's where you're going to operate at the preferred conditions. Okay. Now we'll switch over to wire-to-water efficiency. This is going to include the effect of the electric motor that's turning the impeller. And there's a formula for that. If we know the flow rate in gallons per minute and the differential pressure increase across the pump, and we know the wattage that the motor is drawing, we can put it into this formula and calculate the wire-to-water efficiency. Now, I do want to emphasize that this is not a fixed value. I can't say that a given circulator is 30% wire-to-water efficiency. It will vary, and actually you can see this blue or this purple colored curve over here. This is the wire-to-water efficiency of, again, a small wet rotor circulator, typical zone circulator. And you can see right here, it peaks out, let's say like at about 9.5 gallons per minute, and the peak efficiency is about 22%. That probably will surprise some of you. You're probably thinking 80, 90% efficiency because you're used to numbers like that for boilers. Well, unfortunately, it's nowhere near that. This is telling us that at peak efficiency, that circulator is converting about 22% of the electrical power going into it into head that's been added to the fluid. And actually, if we operate at other conditions, and I've got another slide that shows that, you'll see that the efficiency drops off in both directions. And again, this is a reminder, you really don't want to operate a circulator up here near the upper end of its pump curve or near the run-out point, because you can see here the wire-to-water efficiency drops off quite a bit. In this case, I calculated at a flow rate of, in this example here, if we had a flow rate of 5 gallons per minute going through a 3/4 inch copper circuit, 200 feet long, with a circulator that was 25% wire-to-water efficient, how much electrical wattage would that pump require? Well, looks like about 33 watts. So again, you can manipulate this formula to either calculate the wire-to-water efficiency if you know the wattage, or vice versa. If you're looking for the wattage estimate and you know the wire-to-water efficiency, you can use that formula either way. Over here on the right shows a situation. Let's say we had a circuit with this kind of a head loss curve. It's a steep curve, and it intersects pretty close to the upper end of that pump curve. Well, we'll find that point. We go down to the wire-to-water efficiency curve, the purple curve, and then over. Looks like about 12% wire-to-water efficiency if we were to set up this scenario here. On the other end, if we had a shallow system curve and it intersects the pump curve here, well, let's read up to the purple curve and over. Well, we're up to about 14%. The best situation would be this green curve. It intersects right there near the center of the pump curve, and I set that up so it falls right under the peak of our efficiency curve. And again, we're at about 22% there. So ideally, if you look at this graph on the right, the general guideline I suggest is to keep the intersection between the circuit's head loss curve and the circulator that you're going to select for the system. Ideally, you should be in the middle third of the pump curve, that intersection point, the middle third of the pump curve, because you can see here, that would put you up in this region, not necessarily at the best efficiency point, but reasonably close to it. Let's talk about some of the new circulators. They oftentimes are referred to as ECM circulators or smart circulators. ECM stands for electronically commutated motor. Real quickly, we've got a permanent magnet in the rotor, and we're going to make that permanent magnet spin. And we're going to do that by changing the magnetic polarity on the stator poles. And these are just windings of copper wire. You can actually see them right here. And we're going to use a microprocessor that can reverse the current direction very, very quickly. And think about it in millisecond time. And by changing the magnetic polarity of these stator poles, we can make this magnet spin. And we can control the rate of that spin over a very wide range. So the consequence is we have a wide range of speed control. We have a wide range of pump curves that we can operate at. Each one of these red curves here, think of it as a curve at a specific speed. Okay? And actually, you can kind of blend those together and call that an operating region. And in theory, the operating point between the circuit's head loss curve and the pump curve could be anywhere in this gray region. Notice the manufacturer, though, has precluded up here and down here. They don't want you operating that circulator at extremely low efficiency points. Here's the lineup as of, I guess I could say as of next week. This is the lineup from the major manufacturers of circulators. Taco's added a couple circulators to its lineup this year. This one is basically a temperature or delta T function. This one is delta P function. And just a couple weeks ago, I saw this in one of the trade journals. I wanted to add it. It's going to be coming out next week at the ASHRAE show from Aquamotion. So you get a wide range of product in the residential, light commercial sector. Here's a lineup in the larger, bigger brother to these smaller pumps. Again, most of the major players are there with products that can go up to several hundred gallons per minute of flow rate. And again, they have a whole family of these larger circulators. Check them out. Okay, now, one of the Achilles heels of any circulator is a condition called cavitation. We want to avoid that if you don't want your impellers to look like this. Now, looking at a photo like that, you might say, well, what was going through that circulator? Was it a mixture of sand and water that just eroded that away? And no, that could be perfectly pure water going through that circulator. But what's happening is that the water is literally boiling as it hits the impeller. You might say, well, you know, my system doesn't operate at 200 degrees or 212 degrees. You can make water boil at 50 degrees if the pressure is low enough. So what we have to avoid is a condition where the water reaches what's called its vapor pressure, because that's where it boils. When water gets down to its vapor pressure, you instantly get vapor pockets forming, and that's not the damaging part. What happens is eventually the pressure increases, those vapor pockets implode. And if you've ever heard that, it sounds literally like somebody's taking a hammer and beating on the pipe. It's very noticeable. And those implosions are very violent, but at a very small level. I was once reading about a cavitation, and it suggested that as these vapor pockets implode, as they collapse on themselves, they can actually accelerate tiny amounts of water to 2 times the speed of sound. So imagine a tiny little amount of water hitting a metal surface at 2 times the speed of sound. That's going to cause erosion. And you can see the results here in this impeller as well as in the volute here. Now, there's another kind of cavitation that I'm sure many of you have heard. It's called gaseous cavitation. This is where air molecules, nitrogen and oxygen, that are being carried along with the H2O molecules, it's where they actually come out of solution. And you'll tend to get gurgling sounds inside a circulator. A good air separator will get rid of those gases, and that gaseous cavitation will go away. That's not as damaging as the vapor cavitation. Now, to predict cavitation, again, we look at the math here, but don't get concerned about this if you don't like math. There's a couple concepts here, and I just want to explain them, and again, I want to point you back to Hydronics 16 to get into more detail. It's called net positive suction head, and there's 2 net positive suction heads that we want to talk about. The first one is called net positive suction head available. And it says here, this is a precise description of the state of the fluid in a specific piping system as that fluid enters the circulator. And here's a formula that lets you calculate that. But instead of spending a lot of time on these parameters, let's talk about this. Net positive suction head available is totally determined by the piping system. This has nothing to do with the circulator. It is a condition that is set up by the combination of the piping system, pipe size, pressure, flow velocity, the operating conditions, and the specific piping system will determine net positive suction head available. Okay? And again, we could go through this quickly, but to calculate this, to calculate pretty much any formula, you have to go out and gather information. And the information we need is the flow velocity, the pressure at the inlet of the circulator, the vapor pressure of the fluid, which is dependent on temperature, and the density. So you look at a formula like this and you say, well, I've got to go get all these things before I can plug the numbers into the formula. Well, for water, here's a curve that lets you get vapor pressure. You find the temperature of the water that you're working with, you go up to the curve and read over, and you read the vapor pressure. Here's a curve that lets you get the density of in this case, water. Again, if you're working with a different fluid, you have to get different curves for the specific fluid. If it's a 30% solution of propylene glycol, that's going to have a certain vapor pressure and density. If it's a different concentration, those numbers will change, and the glycol manufacturers put out pretty extensive data on that. So that information is all available. You also have to calculate the flow velocity, and that's based on the flow rate and the pipe size. So, you know, kind of the nuances of working with a formula like this is essentially going out, is sort of like building something where you have to get all your tools and all your materials gathered up, and then you finally build it. Well, to evaluate that formula, you gather up all this data, you plug it in, and you get a number. Now, in this example here, we have a circulator. We've got water at 140 degrees Fahrenheit, 8 gallons a minute, 1-inch copper tube, and the pressure gauge at the inlet of the circulator is reading 13 psi. So ultimately, I gathered that information, put it in the formula, and we get this number here, 58.4 feet. That's the net positive suction head available. And you're probably saying, what does that mean, 58.4 feet? What does it mean? Well, by itself, it doesn't really mean much at all. What we're going to do next, though, is we're going to compare it to something called net positive suction head required. Okay? This is totally determined by the circulator now. And manufacturers will test circulators, and they will come up with another curve. Okay, we've talked about the pump curve. That's the red curve here. But manufacturers will also plot out a curve called net positive suction head required. You tend not to find these curves for small circulators, but for commercial-sized circulators, take a look. There's usually another curve or data where you can find this. This is the minimum value of the net positive suction head that you have to provide in your piping circuit in order for this circulator to avoid cavitation. In other words, if the net positive suction head available that we just calculated for the piping circuit, if that is greater than the net positive suction head required by the circulator, then you're in good shape. You're not going to have cavitation. But vice versa. If the net positive suction head required by the circulator is greater than the net positive suction head that you're making available in the piping circuit, instant cavitation. So it's basically a matter of calculating that net positive suction head available and then looking up the net positive suction head required for the circulator, and you want to make sure that the available is greater than the required. And generally, we like to have a safety factor of about 2 feet of head there. Okay? Now, there's some other things. I'll call this kind of the qualitative evaluation of cavitation. Everything that talks about over here on the left side, these are things you do not want to do. These are all design details that invite cavitation. Things like putting a throttling valve on the inlet of a circulator, pumping towards the expansion tank, operating your system at very low static pressure. These are all things that tend to make the fluid more likely to boil as it goes into the eye of the impeller, and that condition is called cavitation. So over on the right side, I've tried to improve all those. We're pumping away from the expansion tank. We're at a lower temperature and a higher static pressure. We're basically not messing around with the inlet side of a circulator. That's an important idea. Don't put a circulator 2 inches off the side port of a T. Don't put an elbow immediately upstream of a circulator. These are all piping details that cause turbulence and cause drop in pressure, which means that the net positive suction head is going down, and that's the wrong direction if you're trying to avoid cavitation. Okay, so basically avoid everything on the left, do everything on the right as possible. I'm sure many of you have heard this concept of pumping away. Dan Holohan really has done a good job of promoting that concept over the years. I just want to clarify, when we say pumping away, what do we mean? Are we pumping away from the boiler? Well, not necessarily. We're pumping away from where the expansion tank connects to the system. Okay? That's the general idea. You always want to locate the circulator relative to the expansion tank so that the expansion tank is close to the inlet of the circulator. And what that does is it causes an increase in pressure in the system when the circulator is operating. And you can see this red profile here. This represents just the static pressure. And it's let's say it's 10 psi here. Okay? When we turn on the circulator, at almost every location, the green line, the dashed line there, is higher than the red line. That means there's been an increase in pressure in that piping system, and that gets you farther away from the cavitation situation. It also helps, if there is some dissolved air in the liquid, it also helps to suppress the bubbles from forming. Now, ultimately, again, a good air separator is going to take that out. But if there is some air in the system, the higher the pressure, the less likely that air is to cause what we call gaseous cavitation earlier. Now, this shows the bad situation down here, lower right. Notice that I've moved the expansion tank to the discharge side. So instead of pumping away from the expansion tank, we're pumping towards the expansion tank. And I hate to say it, but there's a lot of residential systems out there with that detail. And it's more about just the convenience of where somebody hangs the expansion tank in the system. What that does is it causes the pressure to drop whenever the circulator is on, And again, anything that causes a drop in the pressure gets you closer towards a boiling condition and potentially closer towards cavitation. So pump away from the expansion tank. And as you look at your schematics, as you make sketches of systems, keep that in mind. A couple other things I'll address real quickly. There are some applications where occasionally you'll mount circulators in series, like shown right here. When you do that, it's really important that the flow direction arrow on each circulator points in the same direction. And you might say nobody's that dumb. Nobody's going to mount those so that they're either pumping in opposite directions, you know, pumping towards each other, pumping away. I know of at least three situations where that's happened and has been corrected. So make sure those arrows point in the same direction. Real quickly, if you know the pump curve for one circulator and you put two of them in series, you just double the height of the pump curve at every flow rate. So here, for example, we're at about 16.5 feet ahead. So I drop it or push it right up there to double that, okay? And that's true at all these flow rates. So you get a new curve here that would represent the, I'll call it the net curve, the effective curve for two pumps in series. Again, in theory, you could put 3 pumps in series, 4 pumps in series. I kind of question that unless there's some really exotic application. Generally, 2 pumps in series is adequate. And you might say, well, when should I do that? Well, you want to do that when you want a very steep effective pump curve. In other words, you have some application that has a very high head loss characteristic at relatively low flow rates. Drain-back solar systems are a good example of that, and also geothermal heat pump systems. Excuse me. This graphic on the left here shows a drain-back system. We need those 2 pumps in series. Well, I say we need it. There are single pump solutions for this today, but customarily, I'll say 2 pumps in series like this was a common approach, and that's because we actually have to lift the fluid from this static level up through the collector. Okay. Another application where you'll see pumps in series are in the pumping stations that go with geothermal heat pumps, and that's because a typical earth loop can have a pretty high flow resistance characteristic. So putting 2 pumps in series, and you notice here they're in what I call a push-pull arrangement, and that's fine. You don't have to bolt them flange to flange to have the same effect. So whether they're 2 separate mountings, as it's shown here, or whether they're bolted flange to flange, what we call close coupling the pumps, you'll get the same effect either way. You can also put circulators in parallel. Basically, that doubles the flow rate at each head. So instead of doubling the height of the curve, we double the width of the curve. Here's a nice photo of a couple circulators mounted in parallel. Notice there's a check valve downstream of each one of those. Okay. You can also see there's kind of a symmetrical piping set up here, so that each circulator has about the same flow resistance in that piping assembly. It is important to put those check valves in. I will encourage you to have at least 12 pipe diameters of straight pipe between the discharge of a circulator and the inlet of any check valve. That's so the check valves don't rattle. If you put the check valve right on the discharge of the circulator, you're getting turbulent flow coming out of the circulator at times, and that'll make that check valve rattle. Ask me how I know that. Okay, differential pressure control. Anytime we're doing valve-based zoning, could be zone valves like this. It could be manifold valve actuators, or it could be thermostatic valves on panel racks. These are all examples of valve-type zoning. As zone valves close, differential pressure across the circulator increases on a fixed-speed circulator, and we need to know how to deal with that. Here's what it looks like. Here's 3 zone valves with a fixed-speed circulator. This blue curve right here, where it says 3 zones on, that represents the system head loss curve with all 3 of these zone valves open. And we get an intersection point right here in a certain flow rate. Okay. Now, if we close one of those zone valves down, the system curve gets steeper. Think of it as a 3-lane highway where one lane just got closed down and you have a 2-lane highway. You have more flow resistance. So the operating point moves from here up the pump curve to here. And I like to think of that movement in 2 components. The movement to the left is fine. We want to go to a lower flow rate because we just shut down one of the zones. We don't need the pump to produce the same flow rate. But the movement upward is undesirable. We don't want a change in pressure between the supply header and the return header. Now, inevitably, you will get that change in pressure if you just do the system the way it's shown here. What that means is that the flow rate through the two zones that remain on is going to increase. That's because there's more pressure between the supply header and the return header. If we close another zone down, we're going to get a further increase in differential pressure, and that's going to increase the flow rate through that one zone that's still on. And you might say, what's wrong with that? Well, small amounts of increase in flow velocity probably won't be a problem, but when you get to the point where you can hear the fluid going through the zone valve or the piping, or you get into flow rates, let's say, or flow velocities up around 6 feet per second or higher, you can actually start eroding copper pipe. So it's not good to operate systems at excessively high flow velocities. In smaller systems, we try to keep those piping flow velocities no higher than about 4 feet per second. Now, one of the things you can do to minimize this vertical movement of these operating points as zones close is to select a circulator that has a relatively flat pump curve. You can see here the green curve produces less increase in height as we go from 3 zones on to 2 zones to 1 zone on compared to the red curve. I will tell you, avoid high head circulators in systems that use valve-based zoning, because if it's a fixed speed circulator, it's going to create these high departures in differential pressure as you close down those zones. So traditionally, a flat pump curve is a better selection. Another concept I want to throw at you is think about hypothetically, what would be an ideal pump curve? If you could create the perfect pump curve for a zone valve type system, how would it look? Well, pretty simple. It would be a perfectly flat line. What that does is it allows those operating points to move left and right. In other words, it allows the system to change flow rate as zone valves open and close, but it does not change the differential pressure across the headers. What that means is that when a given zone valve closes, the flow rate in the other zones has absolutely no change whatsoever. Close down another valve, the flow rate doesn't change. All right? In other words, each zone operates at a very stable flow rate irregardless of what the other zones are doing. Unfortunately, you cannot create a perfectly flat pump curve for a fixed speed centrifugal pump. And I want to emphasize, fixed speed centrifugal pump. Now, there is another technique that's around, and that's to install a differential pressure bypass valve. And in effect, what a differential bypass valve does, think about a relief valve in a system. You have a spring holds the plug on the seat of the valve. When you get to a certain pressure, the pressure of the fluid forces that plug of the valve open against the spring. Well, that's what happens in a bypass valve, except instead of spilling fluid out of the system like a relief valve does, in effect, it just allows fluid to move from the supply header to the return header. The net effect that it has is you can think of it as flattening the upper part of the pump curve. Right here is where the valve starts to open, and if you look at this black line and where the operating points are tracking along it, and imagine that you now have a pump curve that it starts here and it goes upward, but once that valve starts to operate, and you can control that by the adjustment of the knob on the valve, once that happens, you get a relatively flat remainder of the pump curve. Now, if you look at that graph close, you'll see it does go up a little bit to the left, okay? But this controls differential pressure, but I use the term it does it parasitically, okay? It basically throttles away the excess head that the pump is producing. Remember, this is a fixed-speed pump now, fixed-speed circulator, I should say. It throttles that extra head away and just converts it ultimately into heat. So it's sort of like driving your car. If you wanted to drive your car at 40 miles an hour, you shift it into drive, you push the gas pedal to the floor, you go to full power on your engine, and then you use the brakes to hold the car at 40 miles an hour. Now, it's not a recommended way to drive a car, and I don't want to say this doesn't work. This is a solution. It's been around for quite a few years, and it will still work today. And if you are working with a fixed-speed circulator, this is the preferred way to control differential pressure when you have any type of valve-based zoning. Okay? But there's another approach that is developed only within the last few years when variable speed circulators that can operate on constant differential pressure mode have come into the picture. And to kind of give you an example, let's assume we have a 4-zone system, 4-zone valves, and we have a pump here that's at a full speed condition. This dashed line will represent full speed, and this dashed blue line represents the system head loss curve at all zones open. Well, there's the operating point. All right, we close the zone valve down. The dashed blue line is going to shift up to the solid one. In other words, if this was a fixed speed pump, this point is just going to migrate over a few seconds up to here and sit here. But with the pumps that are on the market now, they have the ability to sense the differential pressure they're operating at and compare that to some set differential pressure. You've programmed in some type of a setting. Let's say it's 3 psi. Well, as this point starts to depart from that setting, the pump understands that. Just like the cruise control in your car understands when the car's deviating above or below the speed that you've set, and it immediately will change the speed of the motor to correct that situation. Okay, so you can think of this mode of operation in a pump as cruise control for differential pressure. It's as simple as you set the value that you want at a design load condition where all zones are open, and then the pump simply constantly strives to hold that differential pressure regardless of how many zones happen to be on or off. And it's an excellent application for a system like this. I'm showing some panel reds here with a manifold. Here's that variable speed pump, and here's a hydraulic separator. This, if you look at the dashed black lines, that represents what I call the common piping. Constant differential pressure control is excellent when the head loss in the common piping portion of the system is relatively low compared to the head loss in these branch circuits. Okay, so when you have a fairly short and generously pipe-sized system down here, a hydraulic separator has very little head loss through it, and a manifold has very little. So we don't have much pressure loss whatsoever here, okay, or pressure drop, I should say. But we have the majority of the head loss that this pump has to resupply is in these branch circuits. So set that pump up in constant differential pressure control mode, and you've got cruise control all set up for your system. The other mode is called proportional differential pressure control. I don't have a lot of time to get into it, so I'll just say use this when you're dealing with a piping system that looks like this. This is a 2-pipe reverse return distribution system. The characteristic here is we have a much higher percentage of total head loss occurring out in the, what I'll call the mains piping as compared to the branch piping. When you have that, the pump can be set to a proportional differential pressure control mode. We talk about this again in more detail in Hydronic 16, but that is the preferred operating mode when you have that type of a piping system. Last topic I want to jump into is called distribution efficiency. And this is important. If you're dealing with hydronics, oftentimes we get drawn into discussions of efficiency, and usually we're talking about the efficiency of the heat source. And we're kind of neglecting the efficiency of the distribution system. And yet, over the maybe a 20-year design life on a system, that can make the difference in thousands of dollars in operating cost by not getting the right design there, not getting the right circulator. So let's define distribution efficiency and run through some quick examples. And then we'll have some time to take some questions. It's real simple. It's the rate of heat delivery by the distribution system, and we'll do that at design load conditions, divided by the electrical power input to operate the distribution system. Now notice there's nothing in here about the heat source. We don't care whether this is a boiler or heat pump or whatever. It's all about the distribution system. So let's do a quick example. Let's say we have a system with 4 circulators like this. Each of these circulators requires 75 watts when it's operating. And let's say that when they're all running, we're delivering a total of 100,000 BTUs per hour. So the math is easy. We divide the heat output by 4 times 75 watts, 4 circulators, 75 watts apiece, and we get this number here, 333 BTUs per hour per watt. And again, by itself, this doesn't mean anything. What I will tell you is the larger this number is, the better. We're trying to make this number go up, just like a boiler efficiency. We want higher values. So let's compare it to something. Let's compare it to a furnace. Okay? We can say that we have a furnace that delivers 80,000 BTUs per hour, and the blower needs 550 watts. So we do the ratio of those two, and we get this number. And that's definitely smaller than the previous number. So what's the implication? The distribution efficiency of the forced air system is definitely lower than a well-designed hydronic system. And this is a distinct advantage of hydronics that we often don't talk about with clients. The ability to move heat with water, vastly superior material to air, simply because of its physical properties, what's called its heat capacity. And I've got that down here at the bottom. Water has almost 3,500 times more heat capacity than air. So here's what not to do with modern hydronics. This is, I'll call it a wall full of circulators. It looks like a pretty good assortment of make and model and color there. And I won't say that doesn't work, but if we were to calculate out the distribution efficiency of something like this, we're going to find that it goes in the wrong direction. And I'll give you one last example. I actually took a look at a house several years ago that had 40 circulators in it. It was a big house, 10,000 square foot, and 40 circulators. And if we estimated 9 watts a piece, and there was actually a 400,000 BTU per hour boiler plant, we can use those numbers to calculate distribution efficiency for that system. So the system delivers 400,000 BTUs per hour at design load. 40 circulators are running at 90 watts a piece. We get this number here. And that's considerably lower than where we started. So it's actually lower than the forced air system. So the wall full of circulators is really not what I would consider a state-of-the-art approach. You typically do not see this kind of stuff going on outside of North America. So maybe that's a clue that we should stay away from that stuff. Finally, good design will let you get that distribution efficiency up in excess of 3,000 BTUs per hour per watt. I'd recommend you calculate this whenever you design a system. Calculate it and just kind of keep track of it. And as you vary your design approaches, remember, this can make a difference over the life of that system of thousands of dollars in terms of electrical cost. It's especially relevant in chilled water systems because any wattage going into that circulator in a chilled water cooling system is adding to the heat load. Okay? And again, I will tell you, always stress this when you're talking about hydronic systems versus forced air systems with your clients. And I think that's it. So, Bob, I'm going to turn it back over to you. Yeah. Do you want to just leave these up while we take a couple questions?
Yeah, let's do that. Now, I know you're reluctant to get pulling this conversation, but I'm going to anyways. Delta T, Delta P circulators out there. Which one's right? When? How do you decide? What's the pros and cons, advantages, disadvantages? I know that's come up a lot. There's a lot of buzz about that out on the different internet talk rooms and chat rooms and stuff like that. Do you want to weigh in on that, or?
Yeah, it is a lively topic right now. I guess what I would say on it is there's applications for both. There are some good applications for Delta T. One that I've seen of late is controlling a Delta T across the boiler. We've been doing more work with some of the wood pellet boilers and the wood gasification boilers, and they can actually operate it at a pretty decent Delta T. You don't have to limit them necessarily to a 20-degree Delta T. So if you want to operate at, let's say, a 30-degree Delta T, a circulator could be set up to do that. And the advantage is you're going to use less pumping power. And also a Delta T across the Modcon boiler by lowering, or widening, I should say, the Delta T, you're lowering the inlet water temperature to the boiler. And that, in a case of a Modcon boiler, is going to give you better potential for condensation. Delta P, I tend to like Delta P with valve-based zoning because it's an instant response. There's really no sensors involved in that. It's independent of outdoor reset control situations. But again, I want to stress there are good applications for both of those. And I think we're going to be talking about that more. Don't take one of those modes and say that's the only mode that you need for every system. That's generally good advice, I think, in hydronics. Don't pick a single heat source for every application. Don't pick a single method of installing radiant floor heating for every application. My own thoughts is as we go into the future, I think you're going to see circulator manufacturers eventually offer both operating modes, both temperature-based algorithms as well as differential pressure-based algorithms, and maybe even special algorithms like drain-back solar applications or other types of specialized. One of the things to keep in mind with these ECM pumps, they're microprocessors, and they tie into what's called the EEPROM chips. That's essentially the software inside the circulator that tells the microprocessor what to do, just like software tells your computer what to do. So if you can create other operating algorithms, those ECM pumps will easily respond to those, just like your computer will respond to different software.
All right, I think that's and like I say, maybe we'll get to that topic at some point and show some examples of where. Any questions that you've been monitoring that you think would be good here when we got a second?
Yeah, maybe a question or two. Got quite a few people on. Bob or John, concerning a circulator efficiency curve, when you're talking about pure pump efficiency, is that operating point typically similar to the point where you'd also expect most optimal line-to-water efficiency?
That's an excellent question. I've actually never compared those, but I would. I think I'd be safe in saying that they'd be pretty close to each other. Typically, the middle of the pump curve is where you're going to see, from a hydraulic standpoint, the middle of the pump curve is where you're going to see the best efficiency. And I guess if you assume that the actual electrical to mechanical conversion efficiency of the motor stays relatively constant, and I don't know that to be the fact, but if we assume that, then the wire-to-water efficiency curve would also tend to peak out near the center of the pump curve as well. I'll point out that if you buy a little device, a little watt meter, and you can actually buy these devices called kilowatt meters today. You can buy them online for $25. You could put a line cord on a circulator, plug it in, and operate it at different flow rates. If you had a flow meter in the system, you could actually plot those curves out for any circulator you want. You just need flow rate information and wattage, and you could actually check that out.
Okay, very good. Speaking of,
do you see the results?
Yeah, fantastic. Yeah, congratulations to Sunrise Solar, Earl. They're out in Colorado on a big win there. So, and thanks to everybody for submitting their jobs and the entries in that, and keep them coming. Thanks for that. Go ahead, Mark.
Yeah, maybe one more, John. Let's
Sure.
see here. We got quite a few at the very end there. Okay, we'll stick with a couple of circulators in series. Any rules of thumb as to how much you want to space between those pumps to prevent one causing cavitation into the other?
Well, actually, you see a lot of applications where they're bolted flange to flange. What I refer to as close coupling. And again, I've not studied it. I'm not sure if the circulator manufacturers have studied any difference in overall performance. For example, if you were to study the close coupling arrangement and then take the two pumps and separate them by maybe 12 pipe diameters and see if there's any suppression of turbulence coming off the upstream pump that would have a beneficial effect on the performance of the downstream pump. I don't know that to be the case, but generally I think if the two pumps are going to be close together, usually they're going to be close coupled. Some of the geothermal pumping stations that you see in the market today, if you kind of take them apart, look at them, they're set up, one company in particular will go anywhere from one circulator all the way up to 4 circulators in series. And the way they do the 4 circulators in series is they have 2 sets of 2 closely coupled pumps, basically in a push-pull arrangement. As far as I know, most of the circulator manufacturers, if you're going to put the 2 pumps in series, would allow you to bolt them flange to flange. And in doing that, of course, it saves you some space. It saves you the piping in between. And you could do a single set of isolation flanges on that setup as well, whereas if you separate them out, you'd need a pair of isolation flanges on each circulator.
Very good. Okay, one last question. This is on a fixed-speed pump application. If you've laid out your circuit and your pump selection options available to you. Let's say you wanted 10 gallons per minute flow rate, and your various pump options results in a flow rate of, say, 11 or 12 gallons per minute. Is there rules of thumb to say, well, that's good enough, or is it better just to put some other type of device in the circuit, such as a balancing valve? Is it worth that extra cost?
Yeah. Well, again, it's a good question, a very fair question. I don't know of any industry standard on that. It's similar to saying, what's an acceptable safety factor when you size a boiler to a given heat load? You know, some people might tell you 10%, others might say 50%. I'd suggest to you probably plus or minus 10% would be reasonable on something like that. And again, it's not a scientific answer, but you know, if you're looking for 10 gallons a minute and you're getting 11 or you're getting 9, the performance, the actual heat delivery performance of the circuit is really not going to be affected much by that. But on the other hand, if you're looking for 10 and one of the curve crossings is giving you 14 or 15, you're probably spending more than you need to on the pump, and certainly it's likely you're going to spend more in operating that pump than you would. Obviously, I'd rather err a little bit above as opposed to being a little bit low on the flow rate. But you know, if somebody wants a number, I'll throw out plus or minus 10% as a guideline.
Very good. The other questions, anyone that we didn't get to, maybe speaking on behalf of Bob here, we'll make sure we'll get back with each and every question that came in. A number of questions concerns the webinar itself. We do record these and post them onto our website. And so within, I think, a day or two, Rex and Mary have that posted up. So be on the lookout for that if you want to go back in and take a look at what John presented here today. And then lastly, others want a copy of the PDF, which we'll make available, of course, on request. So with that, John, thanks a lot. And Bob, I'll send it back over to you.
Yeah, thanks everybody for attending today. And Siggy will be up at the ASHRAE show next week in Chicago. He's doing, I think you're splitting the seminar with Dan Holohan, aren't you, on your thermal storage, or what's your topic up there?
Yeah, thermal storage. That'll be the morning topic Tuesday morning at the McCormick Center. We're going to take about a 3.5-hour look at different thermal storage applications for hydronics.
Okay, well, maybe the pump guys can come there and ask questions too if they show up. And then everybody's invited to come by our booth at the AHR show. And I guess if that's all the slides you had there, we'll just call this a wrap here, and we'll I think that's all there was, wasn't there, Siggy? On the,
yeah, I can't advance. I think maybe somebody else got control of them. But, yeah, that's it. There's just a closing slide.
Well, thanks. Let's hear from you. Tell us what you want us to do for upcoming webinars.